Okay. Okay, thanks for recording. So thanks for everyone for attending today's visual DOM tutorial. This tutorial is going to be, I think it's going to be easy for most of the people. I will introduce the fundamentals of some computer visions at first, and then I will talk about some of the traditional visual geometry, and then we talk about learning-based visual geometry, and we will find some of the link between the learning-based and the traditional based visual geometry, and they all share some of the basic knowledge and fundamentals in computer vision, especially geometry-based computer vision, and which I will talk later on. So before I get started, I just want to know how many of you have learned computer vision either in Carnegie Mellon or in other previous universities. Okay, yeah. Some of them, yes, some of them, no. Okay, so first, I think everything about that we need to understand about computer vision or later on visual with odometry, either traditional direct methods or even feature-based methods, we all starts with pinhole camera projection model. I think this part is essential for everything. So the pinhole camera projection model is actually a mapping of the 3D point in a 3D coordinate system, world coordinate system, and then later on project this 3D point to the image coordinate system in a 2D. So this is actually a mapping from the 3D to a 2D. So, but this mapping is actually not linear, since we will talk about later, there is some homogeneous coordinate stuff that prevent this from being a linear transformation or linear mapping. So the whole projection process can be described as this x equals to p multiply this uppercase x. The big X represents the 3D world point coordinate, and this little x represents the 2D image points. And P is actually the projection matrix. This projection matrix actually consists of two parts, and we will introduce it later. So in conclusion, the projection actually consists of two parts. The first is actually a world coordinate system. This is in 3D, and we're gonna transform to the camera coordinate system, also in 3D, since we'll do a rigid body transformation from 3D to 3D. And then we'll make this camera coordinate system in 3D and then project this 3D point in the image coordinate system in 2D. So we can see a 2D image, like we said in all the cameras that we have. So first we'll talk about this part, the world coordinate system in 3D, and then the transformation to the camera coordinate system in 3D. So this is a 3D linear transformation. So we want to express this transformation by two components. The first one is the rotation, and the second one is the translation. So the rotation is actually you rotate the axis, the coordinate in three different axes, x, y, and z. And the translation you actually move the camera center or the original point of this coordinate from one position to another. This is called translation. So represented by this graph, we can see from here, there's this is the world coordinate system. There's some point P, maybe some arbitrary point represented as XW. And so this XW is actually coordinate in this world coordinate system. And later on, we will have another representation, another coordinate in this camera coordinate system represented as XC. So this XW and XC will have some kind of a relationship, and which is related by the rotation and camera translation. So we can use a matrix T to represent this linear transformation. So the upper part of this matrix T is rotation matrix. This is 3 by 3 rotation matrix, and also this T vector is a 3 by 1 vector, and this is 0 and this is 1, and we can transform this coordinate from XW to XC by this rotation and translation, and now denoted by this transformation matrix T. Okay, so one of the important thing that we need to notice is that this rotation and translation defined here in this equation actually represent the linear transformation that we did for the coordinate in the world coordinate system, from the world coordinate system to the camera coordinate system. It's not actually the motion of the camera itself. So this R and T does not represent the rotation and translation of the camera itself, but represent the rotation matrix and translation vector that we map the coordinate of the world coordinate system to the coordinate, to the camera coordinate. Okay, so we need to know the difference. So one example to represent this difference is, we can show it here. So we have a 3D point here, and this coordinate is XW, and its coordinate in the camera coordinate system is XC. So we can see here is that we can have XC equals XW minus C, right? If we add these two vectors together, we will have C plus XC or equals XW. So this C vector is actually the translation of the camera itself. So it is also the coordinate of the camera center of this camera coordinate system in the world coordinate system, right? But this is not actually the translation that we map this 3D point XW to XC. Since we, as we talked before, this transformation is actually denoted as T, and T equals to the minus C. So the relationship between the transformation of the coordinate in the world coordinate system to the camera coordinate system and the rotation and translation or the motion of the camera itself is actually inverse the matrix. It's actually the inverse matrix. So they are mutually inversive, right? Okay, so that is to say, if we denote R and T as a transformation of the coordinates from the world coordinate system to the camera coordinate system, the camera motion is actually the inverse of this matrix T. Okay. So that is to say, the rotation RT, or the R inverse, because this is a because for the rotation matrix, the inverse is actually equals to the transpose. And also this translation, the actually minus R transpose multiply T. So this two matrix and vector will be the real motion of the camera. Okay. Okay, so then let's talk about how can we project the 3D point in the camera coordinate system to the 2D point in the image plane or the image coordinate system. So we'll have this pinhole camera model as shown here. So we have a virtual image plane, which is actually so the real image of a 3D point is actually opposite to the original one, but we'll make a virtual image plane in front of the pinhole camera center at here. So in order to make the problem simpler, we'll just put a virtual image plane at here. So this is another illustration graph to show this projection process, and we denote the 3D point as xc in the camera coordinate system. And also we denote the image point as x image in the image coordinate system. Okay, this is the camera center, and this axis. This coordinate is the camera coordinate system, and this small 2D image coordinate is our final image coordinate system. And inside this coordinate system, 2D coordinate system, we have another very small coordinate system. In order to make our derivation simpler, we will use this P as the original to construct another small coordinate inside this image coordinate, inside this image plane. Okay, so this P point, which is the intersection of this principal axis Z and this image plane, is actually denoted as a principal point. And the coordinate is Cx and Cy. So in general, in the ideal cases, actually Cx, Cy is actually half the image size. Because we can see here, this principal point is actually located in the center of the real image plane, the real image coordinate system. Okay. So if we have, if we just look at this plane of this whole camera coordinate system, YCZ, get it here, and we'll have this similarity triangle. And by the properties of the similarity of the triangle, we will have, this kind of relationship that Z over Fy is actually Y over Y, right? And for another plane, ZCX, which is similar to the plane ZCY, we have another relationship for the for that side. Okay. So then we'll have Y equals to Fy multiply Y over Z, and X similarly, which is similar Fx and multiply X over Z. So after this mapping, we actually map a 3D point to the 2D image point. So this is actually a mapping from the 3D Euclidean space to a 2D Euclidean space. So this is actually not a linear process, because in order to make it homogeneous, we actually divided the Z, so making this process, making the whole projection process a nonlinear process. Okay. So because of the homogeneous coordinates, we will have this kind of a nonlinearity inside this projection. Okay, so then we will add the principal point. Take the principal point as consideration. So we'll add the Cx and the Cy in our original coordinates that we get in this small coordinate inside this real image coordinates. This may be a little bit confusing because we construct a very small coordinate, 2D coordinate, in this real image coordinate. So we have to add the coordinate of the principal point, Cx and Cy. Okay, so we denoted the x image coordinate in the image coordinate system in homogeneous coordinate form. So we get the final coordinate of the 2D in the 2D image coordinate system as shown in this equation. Okay, so right now we have the 3D to 3D transformation, and now we also have the 3D to 2D transformation. So later on we'll combine them together to get the 3D to 2D translation. This is actually first rotation translation and then do the projection. So we will write them in a whole complete matrix. Okay. Which is P that we introduced previously. So for this 3D to 2D projection, we can actually make this process and retain the process in a matrix form. And this matrix is actually denoted as K, which is known as the camera intrinsic matrix, or the camera intrinsic parameters, or sometimes denoted as calibration matrix. So this matrix actually diagonal is fx, fy, and 0, and this column will be Cx and Cy if we multiply with the 3D coordinate in the camera coordinate system x, y, and z, and do a homogeneous code and make it homogeneous, and we'll have this kind of final representation for the 2D coordinate system in the image coordinate system. Okay, so this is key. And fx, fy is actually the focal length in x, and y axis, and Cx, Cy is actually the principal point coordinate. Okay, so in ideal form, there will be no distortion for this projection model, but in real, there will be some distortion, radial distortion, etc. And we need to calibrate the camera to get these parameters in order to make the projection process more precisely. Okay. So then we combine the 3D to 3D transformation to 3D to 2D transformation. Hence, we combine the transformation matrix T and the camera intrinsic matrix K and get the final projection matrix P, which is actually P equals K multiply this projection matrix RT. So we'll have a mapping from the world coordinate system in 3D to the camera coordinate system, and then to the 2D image coordinate. Okay, so up to now we finished the camera projection process. Okay, so any question up to now? Okay, so let's continue. So later on, let's talk about epipolar constraints. So epipolar geometry is actually another keystone for the visual geometry, because visual geometry or visual odometry is actually you need to process different frames, multiple frames, not just one single frame, not just the relation between a 3D point and a 2D point, but we need to consider about the relationship, geometry relationship between different frames. So let's first get into the geometry relationship. These two frames can be, coexistent. So these two images, maybe this one is the frame that we take at time step t. This image could be taken at the time step t+1. So this could be two continuous frames, or they could be consistent at the same time. We have multiple cameras, and we get a projection from one point at the same time, one 3D point at the same time to different views. Okay. So the relationship the geometry relationship that we are talking about is actually called the epipolar geometry, epipolar constraint. Okay. So first we'll talk about epipolar line. So epipolar line is actually a very important definition in the epipolar constraint. So we can see that if we project this X point into this first view, we'll have this 2D image coordinate, right? And if we connect this optical center and this 2D image point and this 3D point and form a ray and project this ray to another view, we will have the epipolar line shown here. Okay, so this gives us a very important hint is that in order to find the correspondence, which is the projection of the same 3D point to another view, we can actually look at this point, look at the correspondence in the epipolar line in another view, right? So we all know that finding the correspondence is actually vital to get the camera pose. And for other later on geometry relationship, we all need correspondence. So in order to find the correspondence, we can actually take advantage of the epipolar constraints, the epipolar line. Okay, so later on, let's talk about what is epipole, so a different notation. So now consider about a number of points in the first image, x1, x3, x2, and x3, and we then form various different kinds of rays, ray 1, ray 2, and ray 3, and we project these different rays into another view, into a different image plane. And this 3 projection is actually the 3 different epipolar lines, right? So in some cases, epipolar lines will coincide the same point or intersect at the same point inside this image, or inside this image plane. So this is called epipole. So we can notice that the epipole E2 is actually also the projection of the camera optical center of the first view, right? We project this optical center to a different view where I have the epipole. So next, let's talk about some of the special cases of the epipoles and epipolar lines. So if the camera movement is a pure translation, which is perpendicular to the optical axis, which is like this shown in this image. In this case, the 2 image plane, they're actually in parallel, right? And as a consequence, the epipolar line is actually parallel, and the epipole is actually at infinity, right? Because this L1, L2, and L3, these epipolar lines never intersect at this image plane because they are in parallel. So the epipole is actually at infinity, or you can see it doesn't exist at this case. So this is a very common case for the stereo camera. Since the stereo camera, we rectify it, we can just mix epipolar lines parallel. We can just find the correspondence by searching the one direction epipolar line, which you can find the correspondence much easier, and then you can do the stereo matching, etc. Okay. So another special case for this epipole and epipolar line is actually the camera motion is pure translation along the optical axis. In this case, both optical center C1, C2, and this epipole E1 and E2 will be in the same line, and the epipoles will have the same coordinates in both images, and also the epipolar lines will form a radical pattern like this. Okay, so we can quickly talk about what is epipolar plane. And epipolar plane is actually the plane consists of by the three point. The first point is the 3D world coordinate of this x, and also the camera center C and C prime for another view. Okay, so these 3D points will form a plane, which we call the epipolar plane. And this epipolar plane actually intersect with the two image plane, and we can get the epipolar line at here and here. Okay, so a final definition in epipolar constraint is actually called baseline. Baseline is actually the line which is formed by the two optical center, C1 and C2. And if we connect these 2 points, C1 and C2, we'll have the intersection between the two image plane, and we'll have the intersection at E and E prime, which are the epipoles, right? Okay. Next, we'll talk about essential matrix. So essential matrix actually denoted as E is a 3x3 matrix, which includes epipolar constraints. So essential matrix will actually have some kind of relationship in the epipolar geometry between the two different views. It will have some of the information of the two different views. The geometry, the rotation translation is actually encoded inside this essential matrix. That's why it's very important we need to find the essential matrix, and then we get the camera motions, rotation translation. Okay. Okay. So the essential matrix actually denoted as T cross matrix multiply R, which is actually T cross R. So this T cross matrix actually means that if we do a cross product between the two vectors, we can actually represent it as a matrix multiply a vector. And this matrix is called the T cross matrix. So as here, it's actually T is actually a 3x3 matrix, and R is a 3x3 matrix. And finally, we get E, which is also a 3x3 matrix. This matrix E, essential matrix E, is actually describe the relationship between the two correspondents, X and X prime, which is denoted as here. So this E matrix actually connect these two correspondences, this group of correspondence. So the thing is, if we want to, compute the translation and rotation of the two different views of the camera location and translation, we basically need to first find the correspondence of X and X prime, and thereon we use this correspondence and use this relationship to get the essential matrix. And if we have the essential matrix, we can do a singular value decomposition, and then we can get the translation and rotation. Okay. So besides the essential matrix, we'll also introduce the fundamental matrix, which is denoted as F. F is actually have very special relationship with E, which is denoted as here. So when talking about essential matrix, we usually don't consider the camera intrinsics, but in reality, we always have to consider the camera intrinsics. intrinsic matrix K. So take the camera intrinsic matrix K into consideration and also connect the correspondence, we'll have the fundamental matrix, which is represented as here. So we can see key, and the essential matrix, the intrinsic matrix is actually inside this fundamental matrix. Okay, so the fundamental matrix and the essential matrix will have this relationship because we can see the T cross matrix multiply this R is actually equals to the essential matrix. And then once we have the correspondence of X prime and X, we can actually compute the fundamental matrix F. And once we have fundamental matrix F, we can get the essential matrix E. And once we have the essential matrix E, we can do a single value decomposition, and then we get the translation and rotation. Hence, we can localize our camera. So this is the essential part of visual odometry, of structural motion in general. So E is actually a special case of F because F take the intrinsic matrix into consideration. Okay. Next, there will be some interesting relation between the fundamental matrix and the epipolar line and epipole. So let's talk about it briefly. So like we described before, if we have an image, if we have a point in the one view, we can actually get the epipolar line, L prime in another view. And this L prime is actually denoted as fundamental matrix multiply the image point X in homogeneous coordinate. So according to the epipolar constraint, we will have X prime transpose multiply F and multiply X equals to 0, and substitute this L prime, we'll have this relationship. So this actually gives us a hint that this point X prime actually located inside this L prime, which is true because we actually can't find the correspondence in the epipolar line in another view, right? So it's a function of a line. It's actually denoted by AX plus BY plus C equals to 0. And this parameters of L equals to A, B, and C. If some point X, Y, 1 is actually inside this line, A, B, and C, we can actually have this relationship. This further proves that the correspondence in another view is actually located exactly on the epipolar line of another view. Okay. So we can also have the relationship of the epipole and the fundamental matrix, but I think because of the time, maybe you can read it later on after the tutorial. Okay, so as we said before, in order to get the fundamental matrix, we need to have some of the matches. So if we have enough matches between the two different views, the algorithm to compute the fundamental matrix is called 8-point algorithm, because 8-point algorithm actually is the most fundamental and essential algorithm to solve the relationship between X prime and X, and further get the fundamental matrix. More recently, we have we can actually solve the fundamental matrix with less correspondence. So the recent publication in Parmi actually proposed a 5-point algorithm, which allows us to use 5 correspondence to compute the fundamental matrix. Okay, so later on I will have a very interesting sum which is called fundamental matrix sum, which describes the fundamental matrix, the property of fundamental matrix, and I want to share it with you.
Is everyone ready? Yes, yes. Okay. Right, we're recording. Okay, go. The fundamental matrix used in stereo geometry. A matrix with 9 entries. It's square with size 3 by 3. Has 7 degrees of freedom. It has a rank efficiency. It's only of rank 2. Call a matrix F and you'll see 2 points that correspond. Column vectors called x and x prime. X prime transpose times f times x equals 0 every time. Epipolar constraint involves epipolar lines. Post multiplying f by x results in vector null prime. It's the epipolar line. The other 2 passing through x prime. The 3-component vector of homogeneous design. The left and right null spaces of F are the epipoles E prime and E. All of the epipolar lines should pass through these. Here's a linear spatial example. Take a set of 8-point samples. Construct a matrix, take the SVB and the elements of F with the last column of B. Try to estimate if with a coplanar set of points, your sample set will be degenerate and will not bring you joy. When doing the estimation, if you don't perform range deformation, your epipolar lines and the epipoles will not coincide. But if your C has 3 views, the trifocal tensor is what you use. Constraints from the 3rd view act like glue that has been determined just to you.
Okay, the books mentioned in this song, which is the multi-view geometry in computer vision, and a lot of the material is actually from this book. I think this is the holy Bible in the geometry computer vision, and many of the fundamentals in geometry, computer vision, odometry, structural motion actually came from this book. If you are interested more, you can read that. You can download it freely on the web. So later on, let's talk about RANSAC algorithm briefly. So as we said, if we want to compute the fundamental matrix and later on all the essential matrix and later on the rotation and translation, the first step is actually we want to get the feature, the matching. The correspondence. We want to match the feature and get the correspondence, and later on we can compute the rest of the camera motions, etc. So sometimes, because maybe there's some the mismatching between the 2 frames, we maybe have some outliers. Maybe see this point and this point is correctly matched. You can see they're also the corners of this church. But this point and this point is actually mismatched, right? This point as a church actually matched to the ground, which is obviously wrong. So if we have many outliers, or there's some amount of outliers inside the correspondence, how can we reduce the effect of these outliers in order to get more accurate estimation of fundamental matrix? So this will requires the RANSAC algorithm. So RANSAC algorithm is actually called the random sample consensus algorithm. So in general, what it did is actually we'll first go through a very simple example to see how RANSAC works, and later on we introduce how RANSACs can contribute the computation of the fundamental matrix. Okay, so imagine we have several 2D points, and our goal is to estimate a line, a function of a line, which can actually include most of the point in this data set. Okay, this is actually very similar to the linear regression in machine learning, but slightly different. Okay, so what we do is first we randomly sample 2 points of all the data, because 2 points we can actually get a line, and then we use these 2 points to fit a model, which here this model of this line is actually shown here, and later on we compute how many inliers is actually inside this line model. So we actually define a threshold, which means the difference between the point and the line is inside a threshold smaller than or equal to a threshold, and then we can think it as a inlier. Okay. So in this case we have 6 inliers, right? Then we can repeat this process and then sample the points again. And in this case, we'll have 14 inliers. So even this model is much better than this one. It can fit more data in this small data set. Okay. So this is how RANSAC works. Okay. So now let's see how RANSAC algorithm can be used to compute the fundamental matrix F. So for each iteration, we randomly choose 8 points correspondence from all the point correspondence, right? Because the most fundamental algorithm to compute the fundamental matrix is called the 8-point algorithm. Or we can also choose 5 and use the 5-point algorithm. And with this sampled correspondence, we compute fundamental matrix F. Later on, we count how many inliers can fit in this fundamental matrix, which is to see how many points in all of the correspondence can satisfy this relationship. So X prime transpose multiply F, and then multiply F less or equal to a threshold. So ideally, this equation actually equals to 0, right? We lose in the threshold. We just set the threshold to a very small number, and then we count how many inliers are there for this fundamental matrix. Then we repeat this process for several times and choose the best fundamental matrix and the best correspondence to compute the fundamental matrix. Right. So once we have fundamental matrix, we can just compute the essential matrix if we have the camera intrinsics, right? So we take singular value decomposition of this essential matrix, and later on we can get the translation rotation denoted as here. Okay, so previously we talked about how important it is to match different frames, right, between frames to frame. One of the cornerstone that we build this correspondence is actually we need to extract some of the points that used to do the feature extraction, to do the feature matching, and then to compute the correspondence. So the first question is that if we give two images from two different views, how can we choose the correct points to finish the correspondence searching job, right? So if we look at this image of this mountain and this sky, a lot of snow, etc., we will see maybe it's better to choose some point inside this mountain instead of choosing some point in the snow or in the sky, because if we choose some point at here, we'll easily match the point in the sky here, 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 and here. It's very hard to find a distinct correspondence in another view, right? If we find a point in the peak of the mountain, we can easily find, wow, this correspondence is actually here. We can easily match these 2 points. Okay, also for these two houses, it's similarly. We better choose some of the points from the corners of the window or the house or the roof, right? So this gives us a hint that one point that can compute the perfect correspondence is actually from the corners and edges. So this point is actually called the interest point. Also, this is very similar to the human visual system. We are more interested in the corners and edges, all the points with a lot of texture when we first take a look at some things or some objects. Right. Okay. So there are some state-of-the-art or very successful interest point detector and descriptor. We just listed here, but we're not talking about the details. So we can group these detectors and descriptor into 3 groups. The first one is interest point detector. And we just detect the corners and edges. So two of the most successful point detector are Harris corner detector and good features to check. This is also known as Shih-Tomasi corner detector. Also, we have a gradient-based detector and descriptor, which is SIFT and SURF. So SIFT may be the most well-known gradient-based detector and descriptor. And SURF is actually a variant of SURF. Also, we have some battery detector and descriptor. So gradient computing in the image on the CPU actually consumes some time in the past time, but no longer in at this modern hardware. Still, we want some descriptor or detector which can compute faster. So then we'll have the battery detector or descriptor. So the battery computation is much faster than the gradient computation. So we will have fast and then brief. So fast is actually a detector, detect the key points, the interest point. And brief is a battery descriptor. So a very perfect, very successful combination of fast and brief. It's called oriented fast and rotated brief. So it adds some orientation to the fast and adds some rotation to the brief and makes the detector and descriptor more robust. So that's why one of the most famous visual SLAM algorithms use this ORB feature to do the feature matching and detection. Okay, so that's about feature detector and matching. So what if we don't want to match the features from view to another view? Can we just first detect some of the key points, interest point, corners, edges, whatever, and then just use some algorithm to know the correspondence in the next image without searching the correspondence? So this searching of correspondence actually consumes a lot of time. So a more efficient way is to just use algorithm to compute the location of this correspondence in the next frame, of this point in the next frame. Thus, we can form a correspondence in another approach. So this algorithm is called Lucas-Kennedy algorithms. Lucas-Kennedy algorithms, or LK algorithms. So this algorithm is developed here at CMU by Professor Takeya Kennedy and his PhD student Lucas. Forgot his first name, sorry. So this process, the problem that they try to solve, is also called optical flow. So what is optical flow? Here, we can show here. Imagine we have detect some of the interest point in this image, right? These 4 points. So we can actually compute where the location is in the next image frame. So this vector that moves this point from here to here is actually called optical flow, right? Okay. So we will talk about Lucas-Kennedy algorithms briefly, and imagine we have more than one frame. We have frame 1, 2, and to K. So we have some of the correspondence. We have the brightness consumption, which has the pixel intensity of the 2D projection points, actually does not change. That means the intensity of this point, and also this point remains to be constant. And also we have another assumption in Lucas-Kennedy algorithm, which is a small motion assumption. So if we have the brightness consistent assumption, we can actually makes this equation here and here equal, and we can get the final equation here. So the small motion assumption allows us to do the first Taylor expansion of this intensity, and then make it equation, derive it from here to here, and then we can use the brightness consistent assumption, and to to make this term and this term equal, and thus makes this term equals to 0. Okay. So later on we'll have denoted this this phi f x actually equals to the gradient of the pixel intensity in the x and y direction. So dx, dt, and dy, dt is actually what we want to get. Is actually the velocity, the velocity of the motion of the pixel x and y. Okay. And this phi I and phi t is actually the gradient of the pixel intensity over time. Okay. So make this equation simpler, we will have this equation, which actually can be denoted as the inner product of two vectors, and equals to minus it. And later on we can, so this is just for one point. We can compute this u and v if we have multiple points, right? We have this equation which consists of a lot of points. For example, we take a patch for one of the interest point. Across the point, we take an image patch, which consists of a lot of adjacent pixels for that interest point. So imagine we have n pixels. So we have a matrix size of n by 2. And this UV vector is actually the optical flow that we want to get. And this vector is also known. So we will have this kind of A and B. A is a matrix, and B is a vector, and this U and V is our goal. And we can actually solve this U and V by take the pseudo inverse of this matrix A, right? Denoted as here. Okay. So this here algorithm is actually plays a very important role in both tracking and also visual odometry, especially we don't want to get any correspondence. We don't want to get any correspondence by searching from one view, from one image to another. We can just use this algorithm to compute optical flow, and then we will know exactly where the next point is. Thus, we have the correspondence. And then we can do the similar thing with the correspondence to compute the fundamental matrix, essential matrix, and then the rotation translation, the camera pose. And thus we can finish the camera location or the visual odometry. So the paper is that further describes the Lucas-Kennedy algorithm is here. Lucas-Kennedy 20 years on, a uniform framework. So the paper is published in International Journal of Computer Vision in 2004, and the authors are from CMU. If you're interested in further details, you can read this paper. Okay. Later on, we'll talk about how can we compute the camera pose or the camera depth without even know the correspondence. Okay, this is called direct methods. Okay, so there might be some drawbacks of feature-based algorithm, which is feature-based SLAM visual odometry algorithm, which is compute the feature descriptor are time-consuming, especially the gradient-based features such as it. And these feature-based SLAM algorithms always discard a lot of useful information in the image because it would just take the interest point to do the feature matching and then compute the correspondence and then compute the rotation and translation. But thus, we cannot do the dense correspondence. Okay, it's very hard to do dense correspondence with just sparse features. So one of the possible solutions will be we can use the raw image pixels for the for matching after computing the feature detector. This is called semi-direct methods. So this will solve the problems of the computing the descriptor and also save some time for feature matching. So in order to do that, we can use the Lucas-Kennedy algorithm to compute the descriptors. Okay, after we detect on the interest point in one image. Okay, or we can just direct match the raw pixels without even the feature detectors. This is the goal that we're interested in this part. Okay, so there will be some derivation, but I think this is the last part of the math. So back to our two-view geometry figure. So this view and this view. We now call this view as a reference frame and this view as a target frame. So the same 3D point project to different views as x and x prime. We also have epipolar lines and epipolar pole and epipole, but we're not going to use it this time. Okay. So for a point at the 3D work coordinate system, xw equals x, y, and z. So we can actually back project this 3D point to the 2D point, which is we can represent this xw with this x image reference here by using the intrinsic matrix and the depth that we estimate. And then we can warp the same point that project this point to this view, to the target view, if we have the rotation translation. Okay, but this rotation translation depth actually estimated, not something we already have. It's what we want to get and what we are going to estimate. So, if we finish this warping, we can actually get the whole image if we warp every point as this reference frame to the target frame. So once we have the warping, we will have the photometric loss. You know, we can minimize the photometric loss, optimize the photometric loss, and then we can get optimized rotation, translation, and depth. Okay, So this is actually a nonlinear least square problems. The solution for this problem is Gauss-Newton and Leavenworth-Markov algorithms. Okay. Okay, so that's all for the fundamental of computer vision. We will have all the fundamental knowledge that you would need that you need to understand the famous or state-of-art traditional feature-based direct visual odometry or visual SLAM. So any question up to now? Okay, cool. So let's continue. So next we'll briefly talk about some of the traditional feature-based and direct visual odometry or ORB-SLAM. Okay, the first one is ORB-SLAM. So ORB-SLAM is perhaps one of the most famous feature-based visual odometry, visual SLAM algorithm up to now. So the overview of ORB-SLAM is actually shown in this figure. ORB-SLAM has 3 threads: tracking, mapping, and loop closing. The tracking is actually what we did. We extract the first, we first extract the ORB feature and then initialize the post estimation, and by search the correspondence, get the correspondence, and then compute the essential matrix, the fundamental matrix, and then the camera pose. And also these threads will consist of the track local map and also the new keyframe decision, because we don't want to use every frame. We want to keep the mapping or keep the computing concise. We just keep several frames, which, because if the frame rate of the camera is really high, there will be a lot of redundant frames. So we want to cut this redundant frame just to keep frames which keeps different scenes. So this is called the keyframe. Okay. So once we have the keyframe, we can enter the local mapping thread. And actually this threads runs at the same time in parallel. Okay. So the local mapping, we compute the 3D points by triangulating the feature point, and then we create new points. And then if we have the 3D points, we can actually do the local bundle adjustment, which is optimize the 3D points that we get and also optimize the camera pose we previously compute. And finally, we have the loop closing thread, which optimize the essential graph and also do the loop closure, right? So if we goes back to some of the places that we visit, we can merge the camera pose of the previous estimation in order to reduce the drift of the long-term estimation of the camera pose function, camera pose estimation. Okay. So some of the interesting results here by ORB-SLAM is the correspondence. The correspondence matching here is actually because of ORB feature, because the application of ORB feature, we can actually deal with the scale. We can deal with different scales of the image, even we can see here this image is enlarged significantly comparing with this image. We can still do a good matching between these 2 frames, or even there is some dynamic objects. There's a person walking from here to here, and these dynamic objects actually will actually brought a lot of outliers for this matching. Maybe because of the use of RANSAC, we can reduce the effect of these moving objects, of the outliers. Okay. So we can see this is the results on the KT odometry dataset. It basically fits the ground truth, the estimation. Okay. Okay. Later on, let's talk about the dense direct methods. So the most famous algorithms for the dense direct methods is called DTAM, the dense tracking and mapping. So this algorithm compute the camera pose and the camera depth by minimizing photometric loss. So this is one of the most successful application of the direct methods theory that we previously talked, right? So first, the depth estimation of DTAM is actually, it constructs a cost volume. The cost volume is actually it's actually a summation of the per pixel photometric error. Okay, so the photometric error is what we described previously. We have the estimates the camera pose and estimates the depth. We can warp the point from one view to another, and then we form the photometric loss, and then combine all of this photometric loss of different frames. Okay, sum them together, you can get the per pixel cost volume shown here. Okay, so by minimizing this photometric loss, the cost volume, we can further estimate the depth. So the DTAM actually put a range of the depths. So the minimum and the maximum, we're actually searching optimal depths in this range by fitting it into the photometric cost volume to find the minimum depths that can feed this photometric cost volume. Okay. So yeah, this is an interesting observation at the DTAM. We can show it here. So it takes samples from 3 different positions, okay, A, B, and C. And A, there is no texture. B is a corner, and C is an edge. So we can see that we can easily find the optimal, the local optimum of this cost volume if we have very evident features, very evident textures. So that means even direct methods will also require some texture, okay, in order to do the perfect the photometric cost volume optimization. Okay. Okay. So this figure shows that as we increase the number of the images that we included in the cost volume, we can get better results right here. From here, here, and here. From left to right, we'll increase the number of images that we use in this cost volume. And we can see the more images that we use, the better depth estimation we can get. Okay. So later on, we'll do the camera pose tracking by minimizing the following term. This is also another kind of photometric loss, a variant of photometric loss, which we put it into L2 norm, this one. Okay. So one thing we need to notice is that the DTAM system estimates the depth and the pose in an interleaved manner. So we first estimate the depth And with this optimized depth, we optimize the camera pose. So these are doing interleavely, not at the same time. We don't estimate the camera pose and depth exactly at the same time, but we first do the depth estimation, then with this depth, we do the pose estimation. And then with the pose, we do the depth estimation again, and then doing the interleavely for each frame corresponding, for each two continuous frames coming into the DTAM system. Okay. So next, let's briefly talk about the another direct methods. This is the semi-dense direct methods called LSD-SLAM. The framework is shown at here. This is pretty similar to what ORB-SLAM did. It has a tracking frame, has a tracking shred, also has a depth estimation shred, which is basically the mapping shred, 3D reconstruction shred, and also the map optimization by minimize the photometric loss of many different frames here. So one difference between LSD-SLAM and DTAM we previously discussed is that LSD-SLAM is not using every pixels in these images. They just extract some of the pixels which have very high gradient, and then use these images and use these pixels to do the camera pose estimation and the depth estimation. So this is why it's semi-dense. Okay. So optimization goal is also the photometric loss, which is similar to the DTAM. We minimize the photometric loss. We then optimize the camera pose and the depth. All right. Okay, you can see some of the quantitative results at here. So this is a reconstructed point cloud. It's a little bit messy because you just extract some of the pixels with high gradient. Maybe this pixel is not continuous enough. You don't get them as a whole. That's why they look a little bit messy. Right here. Okay. Okay. So finally, let's talk about learning-based visual odometry briefly. So learning-based visual odometry consists of 3 parts in this tutorial. The first is supervised learning-based visual odometry, which we have the ground truth, and then we just use a neural network to regress the camera pose and use this ground truth to do the supervision, and then doing the backpropagation to optimize the width of the neural network, and then to better estimate the camera pose. Right? This is the idea of the supervised learning. And then we also have this self-supervised learning approach. Self-supervised learning approach actually uses the photometric loss. So it does not have the ground truth. So without ground truth, we cannot do a traditional supervised learning. We cannot get the traditional supervised loss, but instead we'll have the photometric loss by warping from one frame to another frame with estimated pose and depth. We can actually minimize photometric loss by doing the backpropagation and then to estimate the camera pose and depth. We also have the hybrid methods, which takes advantage of both camera depth estimation with the learning ability of neural network, and also we take advantage of the traditional geometry methods and combine them too, and get hybrid methods. Okay. So part of this contents will be a little bit similar to what we discussed in last live seminar that I introduced about the direct methods. Okay, but we'll first talk about supervised methods. So the first algorithm I want to introduce and share with you is PostNet. So this is the publication in ICCV 2015. This is one of the first approach to use a neural network to do the camera pose estimation. So the idea behind this algorithm is to use a convolutional neural network and take image as input and regress the camera pose. Okay. And then, since it's a supervised approach, we'll have the ground truth camera pose and use this ground truth camera pose as supervision. We can then get the loss, the supervision loss, shown as here. So this approach actually divide the translation and rotation estimation into two parts, and then link them with a parameter beta, as here. So the network architecture they use is modified from GoogleNet. Okay, so let's see some of the results here. So the quantitative results that I want to share with you is here. It collects some of the data sets by itself. So the data collection process is basically simply use a camera and go outside, take some videos, and use these videos and put these videos into a traditional SLAM algorithms, traditional circle motion algorithm, monocular SLAM algorithms, and then get the camera pose, and then use the camera pose to label the training of the neural network. Okay, so one of the most important thing I want to note is that it uses the traditional structural motion SLAM algorithms to label the videos to train the neural network. Okay, you can see it collects several data sets at King's College, street, hospital, shop, and this church. So this is a bird's eye view, right? And the green trajectory is the training frames. And the blue one is the testing frames, actually this is the blue one, and this is the testing frames in this video. And also the red trajectory is actually the predicted camera pose, is a prediction. All right. So we can see our goal is we want to make the testing frame and the predicted camera pose make them maybe the same, because we want the prediction as similar as the testing frames. Okay, so this is the ground truth. Of course, we want to make the estimation closer to the ground truth. But we can see in this King's College and the street, these two sequences, we can find that the estimation and the ground truth is actually very similar, right? They basically have a lot of intersection, right? But for the old hospital, for the shop, we can see the estimation and the ground truth in testing phase is actually quite different, right? There's a lot of difference between this red points, that red dots and the blue dots. You can see here. But again, here, this church, this sequence, we can find this blue dots and the red dots actually have a lot of similarity, right? So can anyone tell me why this will happen? Any idea? Okay. Nobody?
Yeah, but you should start picking random people.
Yafei, I have a comment.
Yeah.
Is it because the trained model cannot estimate the rotation very reliably?
This is perhaps one reason.
And is there scale drift?
I think they did a 7-degree from freedom align, so they didn't consider about scale in this particular case. So one important reason is that you see distribution of the training and testing is actually very similar, like this sequence, and this sequence. We can easily get some of the results close to the ground truth, right? And here, here, and here. The training and testing actually has a lot of similarity in terms of distribution, right? But in these two sequences, the training and testing, you can see the trajectory will not have so much intersections, will not have so many similarities in terms of distribution. So that's one of the important reasons. And also one of the biggest drawback of this method is that if the training and testing have some difference, larger difference, the estimation will actually fail, right? In this sequence, okay, because the idea is just too naive and too simple. You just input an image, get a camera pose, and use this pose to do the supervision, right? It does not consider about the relation between different frames, etc. So that's why we will have another method called deep field odometry, which is called towards end-to-end video odometry with deep recurrent convolutional neural network, which is published ACRA. Sorry, it's 2017. Okay, so in this approach, one of the biggest contributions they have is they use a convolutional neural network, but instead they don't take a single frame. They take two images together. So we can see that we talked previously in the fundamentals of computer vision is that the camera pose is actually the same. It's a relation between the two frames, just not what one single frame can do, right? So that's why they take two frames into a consideration, put these images inside, put this convolutional neural network, okay? Stack these two images together and use the information of two frames and then put it into a convolutional neural network, 6-layer, very simple neural network, and then put this feature into the recurrent neural network. And also this recurrent neural network will have the information of the next two frames, okay? And then put it inside and then get this camera pose finally. Okay. So as a result, I think because they use the information of different frames of two adjacent images frames, they can improve the camera pose estimation compared with this PostNet that we previously introduced. Okay. So this is experimental results shown on KT. They also compare some of the traditional methods at here, like RISO. And black dots is the ground truth, and the blue line is their methods. Okay. So we can see that the result is not perfect, but comparing with the PostNet, it has a significant improvement. Okay. So the training is using all the sequences other than this 4. So this 4 is used in testing, and other sequences used as training. Okay. So the KT odometry dataset will have 11 sequences in total. They use 7 sequences as training and 4 sequences as testing. Okay. So yeah. Okay. Another approach, self-supervised approach of odometry. And so this is perhaps one of the most famous approach of self-supervised method for learning-based odometry. Okay, I've shared this paper with many people many times, but this is really interesting, and it's played a very important role, I think, in the advancement of the self-supervised learning approach. Okay. So the idea is that the trainees actually use some of the unlabeled video clips shown here. And they have 2 convolutional neural network. One is used to estimate the depth. Another one is used to estimate the camera pose, the rotation translation. Okay, this paper is published in CVPR 2017. Okay, so the key idea is actually very similar to what we talk about in the direct methods. So they use a pose CAN as a depth CAN to estimate the depth of a particular point, and then use these 2 camera poses to project into 2 different frames, IT-1 and IT+1. Okay. Then we can have the photometric loss of these 2 frames. By combining them together and optimize the photometric loss, we can optimize the weights in the 2 neural network and further improve the estimation of the depth in camera pose. Okay, so this is a network architecture. It's also not that complex. Just 7-layer input, 7-layer encoder, and 7-layer decoder for the depth estimation. And also for this pose estimation, so they also have an encoder decoder structure, but in the middle they get the features extracted out and put the fully connected layers and get the rotation translation. Later on, they also estimate a pose and explainability network, which is to exclude some of the pixels which does not fulfill the photometric consistency that we talked previously. Okay, because if there is some moving objects or some parts which does not fulfill the photometric consistency, it will have some of the a bad effect for the overall estimation of the camera pose and depth. Okay. Yeah. So the final paper that I want to share is called DVS. So this is a hybrid approach. I also shared this paper in the last lab seminar, and this approach actually combines the advantage of depth estimation of the camera pose of the neural network, and also the advantage of the traditional visual odometry. Okay. So the overall method here is we actually input 2 frames, stereo frames. They actually learn the stereo in training and testing it with the monocular camera. So okay, so initialize it. So one of the biggest advantage of using neural network to do the depth estimation is that you don't need to randomly guess like what LSD-SLAM and DSO did. These two approaches, the traditional direct approach, will guess camera depths initially and randomly initialize these depths. But this hybrid method, this DVSO, they can get a decent estimation of depths at the very beginning of the tracking. So they can get the depths, and later on, they will use these depths to do the further optimization of a camera pose. Okay, so the rest of the components very similar to what we talked in LSD-SLAM. Okay, take a gate frame and joint optimize the camera pose and depths with photometric loss. Okay. So this is depth estimation neural network structure, and here. Okay, this is results on KT. Okay. They have some of the They have some improvement compared with DSO. Okay. I think because of the application of depths with neural networks. That is major improvement for DSO. Okay, so that's all for the theoretical part, and later on, let's do some coding and relax. Okay. Okay. For those who already have the Epipolar .py, so this Python file, this Python script, is actually tells how to compute the fundamental matrix and draw the epipolar line. Based on the fundamental matrix that we computed. It's actually load two images. The first one, we can load a stereo pair. We can also load two images in the time sequence, right? So if we first load the stereo image pair, the left and right, and then compute the fundamental matrix, compute ORB feature that first, and then match the features using brute force matcher. Once we get that, we can compute the fundamental matrix based on the points that we extract from ORB feature. And then we select some of the inlier points, and then we draw the epipolar line, and then we plot those lines. So if you run this script, make sure you have the correct directory for your data set. So we first load the left and the right, which is a stereo pair. Let's see how the epipolar line looks. So if you run it, you will have some similar results like this. So you can see the epipolar line is actually in parallel. Because as we said, the stereo pair is actually rectified. There's just a very small motion between the stereo pair. We move the camera in the direction which is perpendicular to the image plane, which is the direction of the baseline. Then we can get parallel epipolar line. So if you change the data a little bit, so the KTL is actually the left image, and the KTL1 is actually the image which is next to it. So this L and L1 is actually in the time sequence, right? It's a monocular time sequence images. Let's see how it looks, how the fundamental matrix looks like. So if you ran a script, you have the similar pattern that I have, which you can see the epipolar line is actually in a radial pattern, right? All the epipolar line will intersect in the same point, which is epipole shown at here. And this epipolar line looks like a radical pattern. Okay. Okay. So if you finish this small experiment, let's move to the next. So next we'll see how we can use the extracted ORB feature and match them to see the image matching process, which is fundamental for the essential matrix and later on for the rotation translation estimation. Okay, again, we will load two images. We can load left and right. We can also load left and left one, which is basically epipolar, which is basically a stereo of the two images in the time sequence. So if you run this script, okay. So OpenCV will have some kind of will have some of built-in methods that you can draw the correspondence directly, which give us better visualization experience shown here. So this is basically a little bit similar to what we did in previous one. Previous one we draw the epipolar line, but this time we just connect the correspondence with this line. No, this one is not epipolar line. It's just a connection between the two feature correspondence shown here.
Yafei?
Yeah.
I have a simple question for the epipolar example.
Yeah, sure.
That is show that if we supply two images from two timestamps, I mean the AR image and AR1 image, and we can see where the all the epipolar lines are concentrated to a single point.
Is it?
Yeah, I mean all the epipolar lines are intersection.
For the stereo pair, you mean?
No, just the
for the time.
Yes, this one.
I think yeah, I think this is what we want to get.
Yeah, I mean the intersection point is that should be the principal point of the camera.
Yeah, ideally yes, but I think the motion of this particular case, is a little bit, I think the motion, the translation is a little bit, different from the one that is really perpendicular to the image plane. That's why we can see the epipolar line is not in the principal point, I think. Okay.
And Yafei?
Yeah.
For the feature matching, we are not using the RANSAC method. Is that right?
Yeah. I think the RANSAC is in the fundamental matrix estimation. Yeah. if you take a look at the Epipolar the pi, the computing fundamental matrix is like CV2 the fundamental matrix. And do I have the CV2 FM RANSAC? I think
Oh, that makes sense.
Yeah, use RANSAC to get better estimation of fundamental matrix. I think the algorithm used is a 5-point algorithm that we introduced in that paper. So if you successfully download the Kitty dataset, sequence 09, image 2, I think you can continue with the visual odometry. So the visual odometry part will consist of 2 scripts. So one is the main part of the visual odometry, another one is post-evaluation utils, which some of them is used to read and load and the images, the post. Also, it includes some of the transformation between the quaternion to the Euler angle, etc. So let me just I can show you what it's going to look like. So the algorithm is pretty simple. Just we write a loop, and we continuously read images from this image sequence, and then compute the essential matrix. First, of course, we'll extract features and do the feature matching. After do the feature matching, we compute the rotation translation, and then we transfer this rotation translation to the camera motion, and then store this this camera motion, and also draw the camera motion, and also receive this camera pose to a TXT file. Finally, so if you run this file, you get something. 3 windows. The first window is just to show how the orb feature looks like. You can adjust how many orb feature you want to get. The more you get, the more computational expensive it will be. And also another window shows the matching of the 2 images. So this is a monocular case. So it just match between 2 consecutive frames. And another one shows the trajectory right here. So a little bit slow because written in Python. You can do the same thing in C++ because for the simplicity of the illustration, I decided to use Python to do the tutorial. But it will be the same thing. The Python OpenCV just simply the binding of the C++ OpenCV. If you rewrite it in C++, I think it's going to become much faster for everything. I suppose CSV true odometry. Yeah, I think why maybe did some modification to the original data set.
Yeah, I put a ground truth post,
Yeah.
but you don't need for this code, I think.
Yeah, it would be better if you include the ground truth. You can compare it.
Where's the poses sequence.txt file? Where is this in files folder?
I think it starts in just the same directory as you put in your code. So for my case, I'll get something like
in the sequence 0 line, you can see the image 2 folder, image 3 folder, and there is a file called poses.csv. The poses.csv is the ground truth.
yeah.
Okay.
Here,
So,
for the code, I think you are loading the txt file, not the CSV file.
for my case, you can take a look at the code 112, starting from 112 to 116. It will transform the pose form to the QM format, which is often used. The first one is time sequence, and then the TX, TYTZ, and then the quaternion of the translation. I think we're almost running out of time. Great, seems working. Yeah, I think it's almost running out of time. And first, some of the code is actually from the OpenCV tutorial in Python, and some of the open source in GitHub. And another code repository I really want to recommend to you is shown here. So this one is recently released called PySLAM. It uses Python, basically implement every algorithm, mainly feature-based algorithm. It also have the binding for the backend of SLAM. So this is really big, and I think I recommend you read it after the tutorial. And also, it has the binding for the visualization tool Pangolin. shown here. And also it has a Python binding for the backend of G2O. So G2O is a C++ tool for the backend optimization tool written in C++, but it use a binding Python binding and make it available in Python. So I highly recommend you to read some of the code and run experience it. Also, more importantly, it actually implements some of the learning-based feature and use this learning-based feature to do the visual odometry, as we can see here. Yeah, it supports a lot of features such as ORB, ORBs, ORB2, and also surf, risk, etc. And also it has some of the learning-based features. Like super point. I think Chen introduced it yesterday. Okay, so I don't think we have time for the learning-based part, but if you follow the instruction of the file that I shared, you will find there is an open source implementation for the structural motion learner.
Yafei, since we're out of time, can you add this some info on PySLAM to your slides?
Yeah,
and then
sure.
add the link to the website, and then also kind of can you put the code that you had, and maybe we can just take the kitty, that subsequence, and kind of package that up so it's all in one place so somebody could quickly replicate this next time.
Sure, no problem. Yeah. So one last thing, yeah, I thought we have time to training and testing this structural motion learner PyTorch, but since we are out of time, I highly recommend you to train it yourself and test it yourself. It will give the monocular depth estimation and also pose estimation, all by the end-to-end neural network. Yeah, and trained by the photometric loss that we talked in the tutorial. Okay. Okay. Thanks all for attending today's tutorial, and very sorry for the inconvenience of dataset and the code. And if you have any comment or questions, I'm very happy to answer any questions.